This video is going to be a brief introduction to complex numbers. I'm going to explain to you the general form of a complex number, both the rectangular and the polar form. And I'm going to explain the Eigen diagram and how you draw the Eigen diagram, and also the modulus and the argument of a complex number. The modulus is represented by R, and the argument we can represent by theta, which is an angle, by the way. So the argument is actually an angle, and the modulus is a number, which is the size of something. All right, so let me start with explaining the general form of a complex number. So a complex number, they are called complex numbers because they are a combination of a real number and an imaginary number. So a complex number, let us call it Z. It's a complex number. It can be written in the form A plus BI, where the A here is representing the real part. So this is the real part. A is a constant representing the magnitude or the size of the real part of this complex number. And then this part here with an I, it is the imaginary part. This is the imaginary part of the complex number. Please note that some textbooks use J instead of I. Sometimes I do mix them up. Sometimes you use I, sometimes you use J. Nothing wrong with that. You can use any that you want. What I have here is what we call the rectangular form. So this is the rectangular form of a complex number. This is the rectangular form. For example, I can give an example of the rectangular form. Let's say we have a complex number Z is 5 minus 4i. This is a complex number in rectangular form, 5 minus 4i. We also have what we call the polar form of a complex number. So I'll go to the polar form. The polar form can be expressed in different ways. I think 3 different ways that we can use. We can write Z, our complex number in polar form, as R, and we put this sign, this is like an L, and on top of this sign here, we put our theta, where R is the modulus, and theta is the argument. I shall explain later on how you calculate your modulus and how you calculate your argument, or how you determine your argument. We can also express this. It is still polar form in this form, R CIS theta. The C is representing cos and the S is representing sine. So please take note of that. I is the I for the imaginary part of the complex number. So this is RCIS, then theta. The C is the cosine of theta, and S is representing the sine of theta. This is another version in the polar form. Then another version which is quite useful is Z. It is like you're expanding this version here. If you expand this version, it actually means R cos theta plus I R sine theta. This is another version. Both of all these 3 are actually the polar form. So if you are writing your complex number in polar form, you can use any of these 3. It is acceptable. An example of something in polar form, it can be Z equals to, let's say I put 5 here, cosine of, no, not cosine. I'm going to use the CIS version. So 5 CCIS 20 degrees. This means my R is 5 and my theta, the argument, is 20 degrees. This is the polar form. Sometimes the polar form is more useful than the rectangular form. That is why you can be required to do the conversion from polar form to rectangular form and vice versa. I have done a video where I explain converting from polar form to rectangular form. Check it out. It is here in the channel, but I'm going to put the link in the description below. Now, these are the two general forms of a complex number, the polar form and the rectangular form. Now I'm going to go to what we call the Eigen diagram. So the Eigen diagram. The Eigen diagram for a complex number. So every complex number can be represented on an Eigen diagram. The Eigen diagram is drawn on the Cartesian plane. It is a Cartesian plane, which means we have a vertical axis and a horizontal axis. So this is, I'm going to draw here my vertical axis and my horizontal axis. All right, so vertical and horizontal, this is my horizontal axis. The horizontal axis represents the real part. So this is the real axis. The vertical axis is representing the imaginary part. So we can put I here. This is the imaginary part of the Eigen diagram. If I have a complex number Z, let me use a different pen. Let us say I have Z here, which is 2 plus 3i. This is my Z, my complex number. Z equals to 2 plus 3i. 2 is representing the real part. So I can come and represent this whole thing here on the on this Cartesian plane, which we call the Eigen diagram. So I have a 2. So there is a 2 here and a 3 on the vertical axis or the imaginary axis. There's a 3 here. We can plot a point, this point, which is essentially 2, 3. So this point is 2, 3. These are the coordinates of this point. The 2 representing the real part and the 3 representing the imaginary part. If I draw a line, from the origin, I'm going to draw a line here from the origin to this point here. The line is from the origin to this point. All right, this is the line. If I draw this line from the origin to this point, the length of this line is going to be r. In fact, let me do this. Yeah, let me use a grid pen. If I draw this like this, the height here is our b. From the general form, remember this is like z equals to a plus bi. So this is our b. In our case, this is equals to 3. And this side here, what we have is our a, which is equals to 2. What I have now is a right angle triangle, and this angle here, theta, is our argument. So theta is the argument, and the length of this line, r, which is the hypotenuse of this right angle triangle, that is our modulus. So r is our modulus. R is equal to the modulus. And theta is equal to the argument of this complex number. So what I have done here, I have represented my complex number on an Eigen diagram. So if someone says draw the Eigen diagram, you draw this diagram, you label your theta and you label your r. That's all. That is all you do. How you get r, you apply Pythagoras theorem, because this is the hypotenuse of a right angled triangle. So if you want to find r, the modulus is equal to the root of a squared plus b squared. In our case, this is the root of 2 squared plus 3 squared. So 3 squared is 9, 2 squared is 4, 9 plus 4 we get 13, so this is the root of 13. That is our argument, root 13. That is our modulus, root 13. If we want theta, we know that tan theta is b over a, which means arctan of theta is arctan of b over a. In our case, this means theta is arctan 3 over 2. This is our theta, arctan 3 over 2. We punch in our calculator and we get the theta, the argument, which is the argument. So arctan 3 divided by 2. The answer is 56. My calculator is in degrees, so that is going to be 56 degrees. So 56.30310 to 3 decimal places, 310 degrees. This is how you get your argument and your modulus. It is as easy as this. The modulus, you apply Pythagoras theorem. The argument, you use trigonometry, your knowledge of trigonometric ratios, the tan, especially the tan ratio. But what I drew here is actually a complex number in the first quadrant of our Eigen diagram. We can also have a complex number in the second quadrant or third or whatever. The difference here is, let's say I have 1 here, and this point, let me use this point here. Let's say this point is 4, which is minus 4, and obviously here is 3. The complex number here, let us call it Z2. It will be minus 4 plus 3i. This one is in the second quadrant. Our theta, our argument, please pay attention to this. Our argument, I'm going to use a different pen to highlight this clearly. Let me use this yellow. In this case, the argument, it is this angle here. We measure the angle from the positive horizontal axis in an anti-clockwise direction. So this is our theta. The angle that we have here, we call it theta ref. This is the reference angle. We get this angle from our calculator. It is not the argument. The argument is theta, which is the positive angle that we measure from the positive horizontal axis in an anti-clockwise direction. This is our argument. Such that if I'm looking for the argument of Z2, which we're going, let us call it theta 2. Theta 2, let us start by finding theta ref. Theta ref is arctan b over a, which is 3 over 4. Don't worry about putting the sign. Just use the positive signs. When you're doing this, when you're finding your reference angle theta, just use positive. Such that what we have here is the arctan of 3 over 4. We get 36.870. So this is 36.870 degrees. But this is not our theta. This is not our argument. Our theta is the angle, this angle here, because this theta is in the second quadrant. The theta is going to be an obtuse angle, which means it is more than 90 degrees, but less than 180 degrees. So our theta itself will be 180 degrees minus this 36.870 degrees. This will be your theta, the argument for this. You apply this notion all, whether you're in the third quadrant or the fourth quadrant, just know what to do. In the third quadrant, you say 180 plus your reference angle theta ref. In the fourth quadrant, you say 360 minus theta ref. So in here, your argument theta will be 360 degrees minus theta ref. Very important to notice that. Okay, let us calculate what we have here. This is 180 minus 36.870. 36.870. We get 143.130 degrees. This is our argument. It makes sense because it is more than 90 degrees. It makes sense because it is less than 180 degrees. Very, very key. This is how you draw the Eigen diagram. This is how you evaluate your argument, which is the angle, and this is also how you evaluate your modulus, which is the length of this vector here that we drew. All right. Let me just finish here by just writing the formula. If we have for Z equals to A plus BI, R, the modulus, is the root of A squared plus B squared. This is the modulus. The argument, for the argument, we're going to find theta ref. What I'm putting here is for the reference angle that you get from your calculator. This is the arctan of B over A. I just want to mention here that use positive numbers. Use positive numbers. All right. Otherwise, that's it for this video. I have explained the general forms of complex numbers, which is the rectangular form and the polar form. I also explained how you draw or how you represent a complex number on an Eigen diagram. I have also explained how you evaluate or how you determine the modulus of a complex number R and the argument of a complex number theta. Please subscribe to the channel, give the video a thumbs up, and share with your friends. Otherwise, thank you for watching.